Afternoon again. So today we are going to start a new subject. It's not a new subject, but we are going to add on top of what we have learned or covered so far. So far, we were interested in looking at the system from a first law point of view, right? Energy interaction in the form of heat or in the form of work, in and out in both forms, right? And we were interested in the stored energy in the system, right? And we introduced some definitions and formulas and laws to tackle those kind of problems. Now you're gonna add a new concept on top of those definitions and formulas. All right. It is called second law of thermodynamics. Okay. Second law of thermodynamics. Highly recommend you to read what it means. Okay? I will try my best to explain what it is. It's basically irreversibility in the system. So every system, any device, any state, any cases, okay, it generates irreversibility, meaning that we have some losses. To heat, to pressure, and other terms that we lose during the process, from moving from state 1 to state 2 or in any cases. So, and we, at the end of this, we're going to introduce a new property that we haven't learned. Okay? And I'm trying to explain where it's coming from and a couple more definitions. Okay? Hopefully it will be clear for all of you. If you have any questions, you can ask me. Okay? Okay. The second law of thermodynamics. I will start this lecture with the given examples from our daily life and see what actually second law of thermodynamics means from our daily life. Okay? Instead of getting into theory and making more complicated, I might in the future. Okay? But for first lecture, I will start from a basic. Okay? So we will start with empirical observation. Empirical observations concerning energy transformation. Second law of thermodynamics can be observed when we have an ice cube, right, in cup of hot tea. Right? Ice melts, right? Hot tea loses heat, cool down, right? Or it can be served two tanks at different levels. They have to get into an equilibrium. Opening in high pressure tank. Conservation of heat inputs into the work output. So most laws, physical phenomena, right? Sciences come from a conservation of energy that we covered so far. It's called first law of thermodynamics. And they are based on experimental results and has a mathematical formula. A second law of thermodynamics is different. It is based on an observation. Okay, it's a fact. It is an observation, and we're going to introduce a couple of statements. Okay, how everything started when they tried to introduce second law into the thermodynamics. Right. So they started questioning some systems. They're called statements and corollaries. They're famous guys, actually. Okay. And a couple of those statements, right? Statements of second law. First one, Clausius statement. Second one, Kevin Planck statement. Clausius states that it is impossible for any system to operate in such a way that the sole result will be an energy transfer by heat from a cooler to a hotter body. Right. It is impossible for heat to travel from a cold temperature to a hot temperature. Right. It doesn't happen simultaneously. You have to force it to happen. Correct? So that's basically what Clausius statements is about. Okay. Second statement. Okay. Let's introduce those terms. Thermal reservoir. Does anyone know what thermal reservoir is? Why is that? Could be stated that way, yes. Or thermal reservoir is an environment. It's infinitely big that you don't make any changes on it. Right? For example, atmosphere. Right? When you start your car, it produces heat. Right? Down into the environment, but environment temperature doesn't change. So in that case, the environment is a thermal reservoir or an ocean. Right? You can change it, but you need to put extreme heat and work, and it will only happen locally. Right? You can't change it universally. Okay. So it is called thermal reservoir. So a special kind closed system from which any finite amount of heat may be removed changing its temperature or to which any finite amount of heat may be added without changing its temperature. Kelvin Planck state. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of work to its surroundings while receiving energy by heat from a single thermal reservoir. So what basically Calvin Planck states that if you need to operate a system, right, a cycle, you need at least two thermal reservoirs, okay, from which you take heat, work, right, heat in this case, and to which you deliver heat. So it's impossible to operate cycle with a single thermal reservoir. You cycle cannot receive and dump heat to a single thermal reservoir at the same time. Okay, in order for us to operate with a cycle, we need at least two thermal reservoirs. We have a thermal reservoir with a temperature TR. Okay. It is connected to a cyclic cycle. Right now, I'm just going to introduce some devices here. Okay. The cycle that produces work in the internally reversible, and this cycle is connected to a processing device which produces work. system with a boundary temperature T. Okay. The cycle, in this case, is called as reversible cyclic device. Okay. It produces work reversible, and the system produces work. Okay. These two systems are connected and they operate together. So this cycle receives the heat from its environment, okay, from a thermal reservoir, and it dumps the heat to this system. The system is combined system with system and cyclic device. So what Clausius says that for any cyclic device, right, the heat interaction at the boundary temperature T can be equal to 0 at most. Okay? So it's maximum 0. Okay, at most. I will come to a point from. Okay, so if I write my energy equation in this combined system, okay, what I have is, right, work combined, work produced, right? These two, work reversible plus work system, right? I call it work combined, is equal QR, the heat entering my boundary, right? QR minus energy stored in the system. Right? And this QR can be written as dQr over T equals dQ over T. If you look at the reversible cyclic device, right? Reversible meaning that it has 100% efficiency. There is no loss. Whichever heat it receives, it dumps the same amount. Okay. So this ratio should be equal to this ratio. Okay? So now I can write my QR in terms of Q, right? So let's do that. Work QI will be equal to, okay, PR dQ over T minus DEC, right? For a cyclic device, for a reversible cyclic device, the stored energy is 0. Remember the cycle, the amount of heat equals the amount of work. The stored energy should be 0. So from it will be 0, right? For a reversible system. So work cycle will be equal to PR, and this integration with 0 or O in the middle represents the cycle. Okay? The cycle. You can call it. You start and go back to your initial position. Okay? So dQ over T. I know that, so look at here, right? I know that temperature is plus. It cannot be negative. It's impossible. Clear? Cannot be negative because we use Kelvin, absolute temperature. Remember, absolute temperature cannot be negative. It can be 0 or 273.15 Kelvin at minimum, right? It is possible. So I know that my work is negative. Okay? So this term is Q over T less or equal to 0 at minimum. Okay? So we came to the same point. What plus U stated. So for a reversible cycle that we said, it is 0, right? It operates at max. So reversible means that the amount of work or energy that you spend to go from point A to point B, by using the same work and energy, you can come back. Right? You have no loss. That's what reversible, internally reversible means. Okay? So most of the cases, that's what we have in real life and real engineering. This is called irreversible. When you have an infinitesimally small irreversibility introduced in the system, this value is smaller than 0. It's negative. Okay, so introduce some irreversibilities and losses during that process. Clear? Okay, so in this case, we started the problem with assumption saying that reversible cycle. So it's 0 in this case. Okay? I will give you more examples on that. Okay. So if we have a piston cylinder assembly, for example, right, with volume A meter cube, okay, and let's extend this to the point where my volume is higher than, bigger than, so let's say x a meter cube and x is an integer. Okay, so it's higher, I extend it. And I put this back where my initial state is. Okay, and this process can be expressed, right? Volume change is 0. Meaning that here, regardless of process, dV is 0. Okay, so it's a path dependent. Okay? Meaning that you can go to Orlando, for example, but there are many ways to go, right? From point A to point B. But depends on which path you follow, mileage, the gas is spent, right? The heat you lose, the irreversibility is changed. And that's exactly what we're doing. Okay. Okay. Reversible process. Give some examples. Restrained expansion or compression. Frictionless motion. Elastic stretching of a solid. Polarization and magnetization effects. Can be stated as a reversible process. So internally, the process I was just mentioning, internally reversible processes. The process which is reversible within the system but it has irreversibilities across the system boundary. Whatever the irreversibility introduced in that system, I push them out and I call that system internally reversible for us. When I wanted to look at a perfect system, that's what I do. Okay. When I say internally reversible, all the irreversibilities are pushed out of my boundary. Okay. And most processes we treat in thermodynamics are internally reversible because we want to simplify the system. Irreversible processes. Irreversible processes. That's pretty wide. Electric resistance. Inelastic deformation. Shock waves. Viscous flow of a fluid. Internal damping of a vibrating system. Fluid flow through valves and porous media or porous spots. Mixing of this similar fluids. It goes on and on. Okay. This here, right? Volume, we start with a volume A, we expanded it and we put it back. The cyclic process, and it's a process dependent and not a path. It's path independent process. Okay? This means that whichever it is, which is volume in this case, right, and volume is a property. Right? If I look at this equation here, okay, equals 0, this tells me that this expression is a property as well. Right? And plus use this volume. I start with a state 1, I expanded it, and I compressed it. I came to state 1. Remember, the property, definition of a property is only related to a particular state. It is not, say, at a different state. Right? The volume change is 0. It's a path independent value, which means it's a property. And this expression tells me that this is also property. Okay? Plus you said that this property or this that expression, integration of dq over t, he called it S, meaning, and he named it as an entropy. So that's where the name comes from. The name is entropy. Okay? And this is kilojoules Kelvin, and we have also specific form of that if we take the integration of both sides from state 1 to state 2. Q over T is finally reversible. It's a specific form kilojoule kilogram Kelvin. Special case. Internally, reversible isothermal heat transfer processes. So from state 1 to state 2, Q over T, an internally reversible process. For an isothermal heat transfer process, I can take this temperature as a constant outside. And this would be Q internally reversible. And in this case, delta S, entropy change, would be Q over T naught reduced to Kelvin. Notice that the entropy change of a system during an internally reversible isothermal process can be positive or negative. Right? Because of Q, right? Q can be negative or positive. Increase of entropy process if I go from state 1 to state 2 and state 1 to state 2, I go from state 1 to state 2 and I come back from state 2 to state 1. But the paths are different. Okay, the first one, the way I go from state 1 to state 2 is reversible or irreversible. Okay, reversible or irreversible. The second path from state 2 to state 1 is internally reversible. Okay. So from the classes inequality, from classes inequality, whether dq over t is less or equal to 0. If I apply this to my path equation, right, from state 1 to state 2 and state 2 to state 1, if I go from state 1 to state 2 by following the first path, dq over t plus, and I come back from state 2 to state 1 with irreversible, internally reversible, not that. So it should be equal or less than 0. I know that this one is delta S, right? It's delta S for S2 minus S1, right? So it's S1 minus S2. So left term, PQ over integration of PQ over T plus S1 minus S2 is equal or less than 0. So that's 2 minus S1 be bigger or equal to less than state 1, state 2 equal to 0. Because 1 to 2 over 2. Okay, this can be written as delta S system, right? Get from state 2 to state 1 equal to this integration dq over t that I introduced from state 1 to state 2, right? They're equal to the plus S generation term. Okay? And this S generation term always a positive. S gen is always a positive or a 0 if you have a reversible or 0. So its value depends on the process and it's not a property. This generation or F pole or delta S system plus delta S surrounding should be positive or 0 if you have a reversible process, right? So this should tell us what kind of system we have. If S generation, okay, if it is positive, right, we have irreversible process. If it is equal to 0, we have a reversible process. And if it is less than 0, it's impossible. Okay. Any questions? We just started in chapter 6, please. Read. Yeah.
So with S gen, you call it input of work or heat?
No, it's a separate term. You don't introduce into system. It's not a energy for not a hero work. It introduces itself to the process. Okay. So it's the inevitability of a nature. It happens to the person. Okay. let's continue on corollaries. Kernel corollaries of second law. Corollary one. The thermal efficiency of an irreversible power cycle is always less than the efficiency of a reversible power cycle. When each operates between the same thermal reservoirs. Remember, in order for cycle to operate, we need at least two thermal reservoirs, right? We cannot receive and dump our heat into the same thermal reservoir. It's impossible. So we need a second, at least two thermal reservoirs. So what Carnot says in the first corollary, the thermal efficiency, if we have an irreversibility introduced in the system somewhere, right? Remember, that's the integration, summation of dq over t. You have a boundary, okay? You have a boundary, right? You have two different environments, two different systems. They receive or send heat work, right, during process, right? So when they introduce heat, right, I take this infinitesimally small steps, right? While I'm moving. So Q, T, and each infinitesimally small step has that on temperature, okay? So that integration, the summation of all these things, right, needs to be reversible or irreversible. If you have one of these, irreversible, your entire system is irreversible. Right? So what Carnot says that if you have two cycles, one is reversible and one is irreversible, right? Meaning that one of those steps, at least one of them is irreversible, that cycle, the thermal efficiency of the cycle is irreversible to introduce to be less than reversible one if they operate between two same thermal reservoirs. Okay, let's get that. So I have an engine here, right? Reversible engine. Irreversible engine, right? They both operate between two thermal reservoirs. The hot thermal reservoir temperature reservoir and the cold temperature reservoir. Right. Hot thermal reservoir from which they receive heat, right? They both receive heat. Okay. And cold, they both come. Okay. Call this one QH, Q hot. Okay, it's for Q hot. Q hot and Q cold. This one produces work irreversible, and work reversible. For a reversible system, the amount of heat it takes, it can give it back at the same amount. Right? And also, amount of heat comes, you can receive. So it's reversible. That's not the case. Okay. What Kana says, we have two cycles, we have two engines with operating with two same thermal reservoirs. The irreversible one is less efficient than reversible. Okay. Corollary 2. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. So basically the same thing, but two engines are reversible in this case. But he's saying that they operate at the same thermal efficiency. Hot temperature. This is what? Two engines. So both reversible engine, reversible engine. Both temperature. Reversible. So both receive heat, H, receive. Amount of work is also reversible. And you can reverse it with the same amount of work. So it's reversible. Right? For irreversible, you either produce less work or you need a higher heat interaction with the system, which is impossible. This will be higher as well. Right? Patients of kernel correlates. Any questions? Yes.
Irreversible engines for like both for the second or array, that be the same engine, or would it be like slightly different?
No, they're same. They're identical.
Identical.
Yeah.
So everything is
Everything is identical. This is identical too, but we introduce irreversibility. That's only the difference. Okay. Let's recall the definition of thermal efficiency. What is thermal efficiency? Does anybody remember? If you don't know what efficiency is, at least you know what it means, right? Efficiency. Efficiency is whatever you put, right, divided by 4, right? If you have a power cycle, your work divided by whatever you introduce in the system, right? So refrigeration or heat pump, other way, right? So that's the efficiency. You don't need to remember or memorize. So thermal efficiency, right? New thermal efficiency, work net. Work is what I am getting from that system, right? Divided by what I am putting. Okay? And this is the case for any system. Let's apply first law. Here on cycle. Okay. Remember, work net for a cycle is Qn minus Qout. So thermal efficiency is Qn minus Qout over Qn, which will be 1 minus Qout over Qn. Okay? We have one. So based on the second kernel corollary, efficiency, the cycle, efficiency of the reversible cycle temperature at boundary, hot thermal reservoir, the temperature boundary at the cold thermal reservoir. Okay. And one of the simplest relationships possible is Tc over Th equals Qc over Qh. Right? For a reversible system, my temperature ratio on a hot thermal reservoir, cold thermal reservoir, to be equal to my heat interaction because it's a perfect system, right? The ratio should be the same. So he says, so therefore, Thermal efficiency for a reversible cycle, 1 minus Tc over Th. Okay. This is the Carnot efficiency. It's also called Carnot efficiency. Okay. Or it's called Carnot efficiency. Maximum efficiency you can get from a system. Okay. If you calculate your Carnot efficiency 60%, and if you calculate and you find your thermal efficiency at 61, it's wrong. It's impossible. Okay. This is a highest theoretical efficiency you can reach. Refrigeration cycle. Refrigeration cycle. Remember, we don't have thermal efficiency for refrigeration cycles of heat pump. What we have is coefficient of performance. Right? So C coefficient of performance, or COP. Okay. For refrigeration cycle, theta is the symbol for COP, coefficient of performance. And QC over the work cycle. And QC work cycle is QA minus Q. So therefore, coefficient of performance for refrigeration at max the Carnot efficiency for a refrigeration cycle will be Tc, right, over Th minus T. Heat pump cycles. Heat pump also have coefficient of performance, COP, and it's gamma. 2H over the work cycle, or 2H over QH minus QP. And therefore, maximum coefficient of performance for heat pump is QH over QH minus QP. Five more minutes. Any questions? I'm sure you have a lot of questions. So make sure you read chapter 6. I cannot promise that you will be clear after reading. Yeah. So try your best, read it, try to pick up, and let me know if you have any questions. Let's look at some examples. Our cycle operating between two reservoirs receives energy QH by heat transfer from hot reservoir at temperature a 2000 Kelvin and rejects energy QC by heat transfer to cold reservoir at heat cold 400 Kelvin for each of the following cases. Determine whether the cycle operates reversible, irreversible, or impossible. A, QH equals 1000 kilojoules, and work cycle equals 850 kilojoules. B, QH equals 2000 kilojoules. QC equals 400 kilojoules. C, work cycle equals 1600 kilojoules. And QC equals 500 kilojoules. D, QH equals 1000 kilojoules. And the thermal efficiency is 30%. Fine. So for case A, okay, well, let's look at it. Okay. I know that my Harnett efficiency 1 minus what? T8, TC over T8, right? Okay. And this is the maximum thermal efficiency I can reach, right? If thermal efficiency is less than the Harnett efficiency, right? Irreversible. if my thermal efficiency equals Carnot, it's reversible. And thermal efficiency is higher than Carnot, it's impossible. At case A, then I will solve it. So case A, my thermal efficiency work net over Qn, right? My work net is given as 850 kilojoules per Qn is 1000, right? 1000 joules equals 0.85. This is my thermal efficiency. To calculate my Carnot efficiency, my Carnot efficiency will be 1 minus T over TA, 1 minus 400 over 2000 is equal to 0.8. So this case A is impossible. Please work on case B, C, and D. So we will go over that in our next class. Okay. Any questions? Okay, this is all for today. I will see you on